Alright, welcome to Chapter 5, Gases. Gases are interesting. They uniformly will fit in any container. They're easily compressed. They also mix completely with any other gas, and they exert pressure on their surroundings. And these properties of gases, make some pretty unique types of things that we can study about them. First off, just to make sure everyone is on the same page, when we're talking about pressure, we're talking about a force over a given area. And that's important when we start to think about the units that we use. When we do and indicate pressure, the SI unit is Newton per meter squared, or 1 Pascal. That is the SI unit. But you will also see it given in some other terms. One standard atmosphere, which is abbreviated ATM, is 100,000, 1,000, okay, you can read the numbers. A lot of pascals. It also is, 1 ATM is going to equal, and these are the important ones for you guys, 1 ATM is going to equal 760 millimeters Hg, or 760 torr, and those conversions there are something that you need to become familiar with. So an example of doing a pressure conversion is if you were given the pressure of a gas at 2 ATM, what would that be in torrs and pascals? How would you set this up? Well, to convert to torrs, you would do something like this. 2.5 ATMs, there's 760 torr per every 1 ATM, so you can have 1.9 times 10 to the third torr. You can double check that your ATMs cancel out, and then you could do the same type of thing to convert it to pascals. These kinds of conversions are very important, especially the converting between ATMs, torrs, and millimeters of mercury. We're going to go through a couple of laws pretty quickly here. What we're looking at is a demonstration of what happens to a balloon that's full of oxygen when it's put in liquid nitrogen. So what happens to the gas in the balloon? Well, there was a decrease in temperature, which was followed by a decrease in the pressure and the volume of gas in the balloon. This is an observation. Okay, you have a balloon that has a particular volume. When the temperature decreased, you now have a balloon with a much smaller volume. The gas laws that we're going to talk about were deduced from observations like these, and they set up mathematical relationships among the properties of a gas, which are pressure, volume, temperature, and moles. So let's go through these quickly. I will say that it's important to have a basic understanding of these, but really the important gas law is the one we'll get to in a moment, which is the ideal gas law. First up, we have Boyle's law. Boyle's law has to do with pressure and volume. Robert Boyle is someone that investigated the relationships between the volume of gas and pressure by changing the height of a column of mercury that was in a J shape and observing what happened. He wanted to see how the level of mercury in the column changes with given pressure. And what he found was that pressure and volume are related, such that if you were to have a pressure and volume of a gas and you wanted to know what the new volume would be if you changed the pressure, you would use an equation like this. So the pressure and volume of a gas at a particular set of conditions is going to be equal to the pressure and volume of gas at a different set. So what does that mean? That pressure and volume are inversely related. An example problem would be if you had a sample of helium gas occupying 12.4 liters and 23 degrees Celsius at 0.956 ATM, what volume will it occupy at 1.2 ATM, assuming the temperature stays constant? Well, you could put in the calculation. You would take the initial pressure times the initial volume, so 0.956 ATMs times 12.4 liters, and put that equal to the new pressure, 1.2 ATM, for the unknown volume. And if you were to solve that out, you should get 9.88 liters. Charles' law is the next one, and this is when he started to look at the relationship between volume and temperature. And so essentially, one thing that's important to keep in mind here is that we're converting from Celsius to Kelvin. If we have a number in Celsius and we want to convert it to Kelvin, we add 273. Also important to note that if I were to give you a number at 0 Kelvin, then that is called absolute zero. And so what Charles' law says is that a given volume and temperature of a gas will equal the same thing if were to change one of those variables. So the example problem here, if you have a balloon at that volume and that temperature, 1.3 liters at 24.7 degrees Celsius, and then you took it and you put it in a temperature of negative 78.5 degrees Celsius, what would the new volume be? So it's important to note here that these numbers are given to you in Celsius and they need to be converted to Kelvin. And if you were to work through that problem, you should see that the new volume is 0.849 liters. The last law that we're going to quickly go through is Avogadro's law, and that's looking at the relationship between volume and number of moles. And Avogadro found that those things were directly related. So here is the sample problem for this one. If you had 2.45 moles of a gas at 89 liters, what will the volume be if you had 2.1 moles of that same gas under the same conditions? This is the same type of problem. You take 2.45, divide it by 89, set that equal to 2.1 over x. If you were to solve that out, you should get 76.3 liters. All of this is leading into the ideal gas law, and that is putting them all together. PV equals nRT. This is really the only one you need to know. Pressure times volume is going to equal the number of moles times constant R times the temperature, where R equals 0.08206 liters ATM per mole K, which is considered the universal gas constant. You must memorize this. Must, must, must. If you're using this value for R, 0.08206 liters ATM per moles K, the temperature also must be in Kelvin. It's very important. Let's look at a problem. We have a tire at 23 degrees C. The volume is 25 liters, and the pressure is 3.18 ATMs. What is the number of moles in the tire? The problem is PV equals nRT. So the pressure times the volume, 3.18 times 25, is going to equal the number of moles, which will be your x, times your constant R, 0.08206. Multiply that by 23 degrees, but remember you need to add 273 to convert it to Kelvin. PV equals nRT. You can solve that and see that N equals 3.27 moles. Here's another problem. Pause this here and try to work on it. For this problem, you need to, you're looking for pressure. So you know that the volume is 304, and you're going to set that equal to the number of moles. So you'll have to take the 5.67 kilograms, convert it to grams, convert that to moles, take that number, multiply it by R, 0.08206, and then multiply that by the 25 plus 273 to convert it to Kelvin, and you should get 114 ATMs. We will stop with the sample problems in this section here for the ideal gas law.